All right, in this section we are going to look at how our calculators can be useful for us and just kind of take a peek at what your calculator is doing when it does it. Computers and technology have made it possible for us to use our calculators to approximate derivatives. When you did derivatives, I want you to remember that derivative is the slope of the tangent line. And remember, if you had a curve, let's say, and you wanted to find the slope of the tangent line, what you're really doing, you can't find the slope at one instantaneous spot. So remember what you did is you took these 2 points, right, and you started with a secant line, and then you moved those dots closer and closer in the line and closer in the line. So eventually they were so close together that they pretty much became the tangent line. Um, and you estimated the slope of that tangent line. So what they're saying when they do the numerical derivative on the calculator is you're moving those points, those 2 points, so that they're like 0.001 apart. And that's what your calculator is doing. And then what it's doing is it's averaging them. So it's overestimating them and then underestimating them and averaging them is pretty much what the numerical derivative does. Okay, just so you know. So first of all, what we're going to do is we're going to find the derivative by hand, and then we're going to use our calculator to find the numerical derivative so that we can see how close we are, okay? Which you're going to find is really, really, really close, okay? So first of all, if you remember, to find the numerical derivative you had, or to find the derivative by hand, you had this formula, the x, and one of h in there. You had this formula. It was f of x plus h minus f of h over h. Okay? So here we go. In this case, I have f of 2 is 2 cubed, which is 8. And then I have f of 2 plus h, okay? Because my x is 2. So, sorry, this should be f of x, not f of h. Sorry about that. Anyway, so my f of x is f of 2 in this case, 2 cubed, which is 8. F of 2 plus h is 2 plus h cubed, okay? I'm not going to take the time to do that, but you really would have to take 2 plus h times 2 plus h times 2 plus h. Okay, I would probably FOIL those two out first, get an answer, and then take 2 plus h and distribute that through. But I'm going to cheat here in the interest of time, and I am going to tell you that when you take 2 plus h and you cube it, you get 8 plus 12h plus 6h squared plus h cubed, okay? And I probably should have done these in a different color, but that's kind of off to the side what's going to get plugged into this formula. Okay, so now what I have is this, the limit as h approaches 0, and unfortunately I can't put 0 right there because I would have 0 in the denominator, but I'm going to have the limit of that. F of x plus h is this quantity right here. So that's my 8 plus my 12h plus my 6h squared plus h cubed minus, this is f of x right here. So that's 8 all over h. Okay, still can't plug 0 in for h because I would have a 0 in the denominator, but this 8 and that 8 cancel. And then what you can do is you can factor in h out of the top. And if I factor in h out of the top, then I will have, and do this backwards, I will have h squared plus 6h plus 12. Okay. Fortunately, these two h's cancel, and now I can go ahead and substitute 0 in for h right there and there. And when I substitute 0 in for h, I get, and I'll just do this, h squared plus 6h plus 12. When I substitute 0 in, I get 12. Okay, so I'm saying that the limit or the slope of the tangent line as it approaches 2, or at 2, I should say, at an x value of 2, the slope of the tangent line is 12 on an x cubed curve. Okay, and I can graph that and I can look at the slope of the tangent line and I can figure that out. All right. Oops, I forgot to do it on my calculator. Okay, then the next thing I want to do is I want you to find that same piece of information on your calculator. Okay, so I want you to do the numerical derivative. This book denotes that as NDER, which stands for the numerical derivative at f of 2. And I'll show you how to do that on your calculators, okay? So I'm just going to go to the main screen here. So we're going to quit out of this. If I go to the main screen and I go to my math key, the numerical derivative is number 8. It's NDERIV down on there, so it's number 8, okay? And then what you need to do is you need to just sort of denote what variable you're using. It's easiest if you just use X on here. Then you're going to put the function in, which in this case was x cubed. Okay, and then we were trying to find it at x equals 2. And if we do that on our calculators, we get 12.0000501. Okay, super duper close to what we got when we estimated it the long way. Okay, so that is that. And then we'll do another one here. This one says use your calculator to find the area of the region R enclosed between the x-axis and the graph of y equals 1 over x from x equals 1 to x equals 4. I'm just telling you that this part of it might not be in your notes, just so you know. So you might need to add that there so that when you go back and look at them, you're not confused. If I'm wanting you to find the area under the curve, I'm really wanting you to find an integral here. Okay, the area under the curve is an integral. This derivative is the slope of the tangent line. So this is asking me to find the area under the curve from 1 to 4 of the function 1 over x. If this is an x right here, this is just going to be dx. Okay, but that's what it's asking me to find. Then you're going to go ahead and you're going to put this on your calculator. This little symbol right here is what's called integral. So you're going to go to that same menu that you were just at. So I'll hit the math key. Integral, you can see, is number 9 right down here. Okay, so I'll go to number 9. Okay, and in this case, I'm trying to go from 1 to 4. And I'll put my function in, and I'm going to use my variable x. If I was using t, I do dt or whatever, but 1 divided by x. And then this is going to be an x, since that's a variable I used in my function. Go ahead and hit enter, and I get 1.3863 about. Okay, so that is my area under the curve, which also tells me the distance that an object moved, just so you know. All right. And then last, just kind of a problem in context so that you know what to do. An automobile is driven at a variable rate along a test track for 2 hours, but its velocity at any time t between the time 0 and 2 hours is given by the function 30 plus 10 sine of 6t miles per hour. How far does the automobile travel during the 2-hour test? Again, if you want to know how far an object moves, then you do integrals. Okay, so you're going to do the integral from 0 to 2 hours of the function 30 plus 10 sine of 6. I'm going to put x in there. Okay, and then I'll do dx. I do need to put this into my calculator. Now, you need to know that with trig functions, sine, cosine, tangent, any of those, your calculator should be in radian mode because that's just sort of mathematical etiquette. Your answers will be slightly different if it's not in radian mode. So it does need to be in radian mode when you're doing trig functions. So it's just because it's the most accurate. Okay, so if you don't remember how to fix that, go to mode, make sure you're in radian. Hit enter. Okay, I'll quit out of here. Again, I'm trying to do an integral because that is what I do when I want to find how far an object moves. Okay, which is also finding the area under a curve. So I'm going to do math. Number 9, I'm going from 0 hours up to 2 hours of the function 30 plus 10 sign at 6x. And since I used x for my variable, it will be dx. Go ahead and hit enter. And you should get 60.26 and your distance for your units. So since it gave you your speed in miles per hour, that means it moves 60.26 miles. Okay, 60.26 miles. All right, and that is that lesson.